Hello, I'm Kirk Weiler, and this is Common Core Algebra 2 by eMath Instruction. Today, we're going to be looking at Unit number 13, Lesson number 6 on sample proportions. Yet again, this is going to be one of these inferential statistics lessons like the last one, where we look to see how or what we can say about a population proportion based on a sample proportion. It's also one of our lessons where we'll be using one of our statistical simulators, which can be found both online, web-based, plus downloadable for the TI-84-3 and 84 Plus calculators. So let's jump in and talk a little bit more about inferential statistics. Now in inferential statistics, you always have a population parameter, like the mean, and then you have a sample statistics, like x bar. And that's what we worked with in the last lesson. In this lesson, we've got the population proportion, or the proportion of a population that shares a certain characteristic, whatever you're studying, okay? And we'll get into that in the first lesson. Now, you'd think we'd come up with a brand new symbol for the statistics, but we don't really. What we do is we just have the same p, but with a little thing over it. We often will call that p hat, like the proportion has a hat on it. And again, the only reason we use different symbols is because we want to make sure that we have a distinction between the population parameter, which we don't know, we're trying to infer something about, and the proportion which comes from that sample. All right, let's jump into the first exercise and see what we're talking about here. A school is trying to determine the proportion of students who own cell phones. They do a survey of all juniors. Notice all in boldface there, all juniors, and find that 168 out of 236 have cell phones. They then take a sample of freshmen, and find that 30 out of 52 freshmen in the sample own cell phones. All right, letter A, calculate the population proportion, P, of the juniors who own cell phones. Go ahead and do that. All right, well again, a proportion is just a decimal percent. I do 168 divided by 236, and that's 0.7118, etc. These are typically rounded to the nearest hundredth, right? Because they're supposed to represent percents, right? So that's, 71% of all juniors own cell phones. And we can actually call that a p-value. On the other hand, in letter B, it says calculate the sample proportion, not the population proportion, p hat, of freshmen who own cell phones. All right, so again, here it's exactly the same calculation. There's nothing funky going on. Right, but we get 0.58, right, which is 58%. Now, what we don't know is we don't know the actual proportion, the population proportion, of freshmen who own cell phones. All we know is the proportion that came from this sampling. But as we've seen, sampling variability, right, very important, sampling variability tells me, well, that 0.58 might be close to the population proportion of freshmen owning cell phones, or it could be significantly off. It's unlikely that it's significantly off, but it could happen. All right, pause the video now and write down anything you need to. All right, so where we're headed, obviously, is to try to figure out what we can say about a population proportion based on a sample proportion. So let's dig into that. All right, in exercise 2, it says, we would like to determine how likely it is that a sample of 52, right, that was the sample of our freshmen, it was 52 freshmen, out of a population with a proportion of cell phone ownership of 71% of 0.71, would result in a sample proportion of 0.58. Now again, let me explain the idea here. The idea here is that we're really trying to figure out whether juniors own cell phones at a greater rate than freshmen. All right. Now, we knew that our population of juniors had a percent ownership rate of 71%. And a sample of freshmen had a rate of 58%. Now you might say right away, well then freshmen own cell phones at a lower rate than juniors. But maybe it was just due to sampling variability that freshmen own cell phones at the same rate as juniors. We just happened to pick a sample that was very low comparatively. All right. Well, we can simulate this. We can see how likely it would be that given a population with a proportion of 71% sharing a characteristic, how likely it would be that a sample from that population of 52 would have a proportion of only 0.58. All right? So for this, what we're going to do, again, just like in the last lesson, we're going to pop out of here and we're going to run a simulator called P-simulation. All right? It's simulating proportions. All right? And let's see how this is done. All right, let's open up our TI-84 Plus. And what we're going to do is go into our programs and we're going to run P-simulation. All right. Now, what it asks me for is the population P. So I want to say that I've got a population with 71% owning cell phones. And I want a sample size of 52, because that's the sample I took of freshmen. How many simulations do I want? Well, I'm going to run 100. This is a pretty quick simulator, but I'm going to run 100 simulations. Here we go. Now, just like before, though, I can cut out a little bit of time by cutting right to the end of the simulation. All right. Well, we're just about finishing up again. So, as we reach 100 simulations, and there we go. It's going to do a little bit of math, and the sample proportions are now in L1. So let's go into that list and take a look. Okay, so we've already sorted this list into ascending order, all right? And what we see is we actually see our first sample proportion, 0.558. Now remember, what's happening here, I want you to understand this, is it's like the computer is closing its eyes. It's like there's a population of people out there, 71% own cell phones, and it grabs a person, 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 right? Gathers up 52 of them, counts the number of them that own cell phones, divides by 52, and gets our proportion. And look at that. Our smallest one had a proportion of 0.558, 56%. Our freshman, that sample was 58%. So we have a sample that actually has a lower cell phone owner rate out of this population with 71% owning it than what we sampled. Now the next one is about 0.58 and the next one is 0.59. So we very quickly get away from that. Just as a side note, on the high end, which we don't really care too much about, we get one as high as 85% owning cell phones, if 71% of the population does. All right, but going back to this, I would say, so it says how many of the 100 simulations had a proportion less than or equal to 0.58? Well, that was 2 of them, okay? 2 of those simulations, the first 2, had a proportion that was less than or equal to 0.58. All right, so let's pop back in here for a second. All right. Only 2 of them. Based on your answer to A, how likely is it that a sample of 52 from a population with cell phone ownership of 71% would result in a sample proportion of 0.58 or less? It's very unlikely, right? It's very unlikely. Only 2 out of them, out of 100. Is it possible that a sample of 52 from a population of cell phone ownership of 71% could have a sample of 0.58 or less? Justify your answer. Well, yes. 2 of them had it. So, it's very important. Statistics and probability are never really ever about proving something indisputably. It's about assigning how likely something is. So in letter D, it says, what conclusion can you make about freshman cell phone ownership compared to ownership by juniors? Explain. Think about this for a minute. Okay, now, remember, what you don't want to conclude is that freshmen own cell phones at a lower rate than juniors. What you can say is, it is very likely that the population of freshmen own cell phones at a lower rate than the population of juniors. Very likely. You know, you could really kind of quantify that. You could say there's only a 2% chance, according to our simulation, only a 2% chance, really, that freshmen own at an equal or greater rate than juniors, right? Again, there's a chance they own it at the same rate. It's a chance that juniors own it at a 71% rate, and so do freshmen. It's just that we got really unlucky with our sample, and that sampling variability kicked in, and we got unlucky and we got a sample that only had a 58% cell phone ownership rate. But it's very unlikely, right? There's only a 2% chance, all right? I'm betting on the 98%. Anyway, pause the video now. Think about what we did before we move on. Okay, let's keep going. An important point about inferential statistics. Inferential statistics is never about proving beyond any doubt. It's never about proving beyond any doubt that a sample either can or cannot come from a certain population. See, in the last problem, we did not prove beyond any doubt that that sample of freshmen couldn't have come from a population that kind of, if you will, looked like the population of juniors, i.e. they had 71% ownership rate. Inferential statistics is all about quantifying how likely, which means we'd have to use probability, because that's what probability does. It quantifies how likely something is to happen. It's all about quantifying how likely it is that it, i.e. the sample, how likely the sample could come from a given population. All right? Keep that in mind. It's always about the likelihood of a given sample coming from a given population. All right? Pause the video now and think about this a bit. All right, let's keep going. Now, one thing I'd like to investigate using our simulator is how important sample size is. All right? Generally speaking, when we are sampling, the bigger the sample size, the better. All right? And I want to kind of check that out. So in exercise 3, it says, let's say that we have a population with a 0.25 proportion of being 65 years or older. So we have this giant group of people out there, okay? And 25% of them are 65 years or older. So it's a giant group, all right? Now what we're going to do is we're going to close our eyes and we're going to grab people, okay? And first we're going to take a sample size of 10. Then we're going to take a sample size of 20, then a sample size of 50, then a sample size of 100. And what I want to see through simulation is how that sample size changes the interval of sample proportions that we get. All right? We may not do all 4 of these on the simulator, but we'll do at least a few of them. Okay? Let's take a look. All right, let's go back into our program. Let's go down to P-simulation. Let's now put in a 25% proportion rate. Let's do a sample size of 10. This is going to be fast Because it's a small sample size, it'll be very quick. Watch it go. In fact, it's so quick, I'm going to make the argument that I don't need to cut to commercial, so to speak. We'll just let it kind of count up. I think what we'll do is we'll do the sample size of 10, and I think we'll also do a sample size of 100. So we'll do the extremes, and then I'm going to give you values that I simulated earlier for sample sizes of 20 and 50. And then we'll be able to see the overall pattern. Now again, keep in mind, with this sample size of 10, it's literally taking this huge population, it's randomly grabbing 10 people, and it's saying, well, how many of these 10 are 65 years or older? Once it figures that out, it then divides by 10 to give us our sample proportion, And look at this, it is just booking. All right, finishing up, and done, and done. All right, let's take a look. Stat, edit. And look at that. No great surprise, we have a number of samples, because we only picked 10 people, where we didn't pick anybody at all that was 65 or older. Now, notice there are no samples. There's no samples with a proportion equal to 1 or 100%. In fact, the best we ever did with 25% of our population, the best we ever did was 60% of our people having being 65 or older. Still, all right, let me pop back in here. The lowest p-value was 0, and I did it again. The lowest p-value was 0, the highest p-value was 0.6, and the range then, 0.6 minus 0, was 0.6. Huge variation. Now remember, the population only had a proportion of 1/4, and yet we took a sample of 10 people at one point and got 6 of them to be 65 or older, just because of sampling variability. All right. Now, what I also did was I did the 20, the 50, and the 100. When I did 20, I got 0 to 0.45, which means my range was 0.45. Now notice, now it went down a little bit, the range, because as soon as you're sampling 20 people, right, that's getting closer to the population. When I sampled 50, I had a 0.08, so I didn't even get one when I was at 50 that had nobody 65 years or older, and that kind of makes sense, to 0.4. So we had a range of 0.32. Let's do one more of these, though, together. Okay, then I'll kind of fill in these numbers. Let's do the one with a big sample size, relatively speaking. All right, so if I go into my program and I go down to P simulation, what I can do now is I can do it one more time with a population proportion of 25%. This time I want my sample size to be 100, so it's pretty big. And I want 100 simulations. And this time, because the sample size is 100, the simulation takes a much longer time to go through it. So yet again, what I'm going to do is I'm going to cut to the end of the simulation. Okay, well, we're finishing up the simulation now as we get into the 90s in terms of the simulations. So let's hit our 100th simulation in just a moment. There it is. And now let's take a look at our results. All right, stat, edit. All right, I'm going to write this down on a sheet of paper really quick. So now our minimum proportion was 0.15, so at least 15% of those surveyed were 65 or older. And our largest was 0.35, so the maximum we ever had was 0.35. So let's summarize all of this. Let's go back into here. And again, let me summarize what we had. When we only had a sample size of 10, we had a huge variation in the proportions that we would get. In fact, we had a range of 0.6, which is large given that the range in P can only be 1 at greatest. Then for 20, I had 0 to 0.45, so at least that cut down my range a little bit, down to 0.45. With 50, we got a lot better. It was 0.08, or a lot more narrow, to 0.40, so we only had a range in 0.32. And then finally with 100, I got 0.15 to 0.35, so that would be a difference of only 0.20. So letter B says, what was the effect of increasing the sample size on the sample proportions that were simulated? Why does this make sense? Well, what would you write down? All right. Well, increasing the sample size decreased the range of simulated proportions and made them closer to the 0.25 population proportion. All right. And you can really see that, right? I mean, 0.6 is a long ways away from 0.25, so is 0. On the other hand, 0.15 and 0.35, well, they're not that far away from the 0.25, right? And why does this make sense? Well, this makes sense because as our sample gets larger, it more closely resembles the population. Or maybe I should say there's a greater chance that it will resemble the population. Right, if I have a sample size of only 10, even with complete randomization, I could still randomly pick a sample where the p-value is very different than the p-value for the overall population. Again, think about this for a moment. There were multiple samples back when we had this sample size of 10 where 60% of the sample was 65 years or older, and yet there's only 25% in the population in general. Yet when I have a sample size of 100, that's not likely to happen. It's not likely that in a sample size of 100, I'm going to pick 60 people that are 65 or older when only 1 in 4, 25% of the population is 65 or older. Not when it's being done randomly. All right? By the way, what this really argues, of course, is that whenever you do a study, the bigger your sample size, the better. All right, pause the video now, write down anything you need to. All right, well, I'm going to clear this out, and then let's keep going. All right, exercise 3 continues to be the same one. Letter C says, run P simulation one more time with a sample size of 50, but for 200 simulations. So we're not going to do a sample size of 100, but we're going to do a sample size of 50, but we're going to do 200 simulations. Using your results, find the value that represents the 5th percentile of p-hat values. Find the result that represents the 95th percentile of p-hat values. Then write the 90% confidence interval for this sample size coming from this population. All right, so let's do one more simulation today. Okay, I'm going to just move this down the screen a little bit so we can see everything. Go to my program. Actually, I got to bring it back up, otherwise I can't even hit the commands. All right, population, we're going to keep it that 0.25. We're going to try to. 0.25. Sample size of 50. And a lot of samples now. We're going to run 200 simulations. Okay, and this is definitely going to take some time. Even though a sample size of 50 isn't too large and they're going quickly, I'm going to still cut the video. Okay, so I'll be back once we're in that 190 range, all right? All right, so we are getting back there. The 200 simulations are almost done. There we go. Let's take a look at our results. All right. Now what we're trying to do here is we're trying to establish this 95th or 90% confidence interval. All right. Now we have 200 simulations. So the 5th percentile is actually the 10th value. So let's go down to that. Let's find our 10th value. Our 10th value, I'm sorry, that's not our 10th value. Our 10th value is 0.16. 0.16. Let me write that down. 0.16. And now to figure out our 190th value, I'll go up here. And we have 0.36. So 0.16 and 0.36. All right, 0.16 and 0.36. And 0.36. This is our 5th percentile by simulation, and this is our 95th percentile by simulation. All right, now I really want you to understand what that means is that if we have a population of 0.25, all right, and we have a sample size of 50, then 90% of the time a sample of size 50 should have a proportion between 0.16 and 0.36. 90% of the time, a sample should have a proportion in that range. 90% of the time, right? So that's a 90% confidence interval on our proportion. Now let's do some inferential statistics. Letter D. If researchers surveyed 50 people walking out of a movie and found that 21 of them were 65 years or older, do you believe this sample came from a general population with a p equal to 0.25? Why or why not? Well, think about this a little bit, okay? All right. Well, let's calculate p hat. There were 21 people that were 65 years or older out of 50. That ends up being 0.42. Now notice 0.42 is not in this interval. And yet, 90% of the time, if the people walking out of that movie theater are coming out, and they're coming out of a population where 25% are 65 or older, then 90% of the time we should get a proportion between 0.16 and 0.36. But we got one of 0.42, all right? So, generally, we should conclude with 90% confidence that the population sampled here does not have a p equal to 0.25. We likely can actually conclude that it's probably higher than 0.25. We'll never say for certain what it is, but what we can say is with 90% certainty, it's not 0.25. And it's not 0.25 because that sample proportion we got was not within the 90% of the samples that we simulated. In fact, it may not have occurred at all. Pause the video now and write down anything you want to, and then let's take a look at those results one last time. I want to see if the 0.42 even shows up. Okay, I'm going to clear this out. I'm going to pop out just for one more minute, okay? because I'm curious. That's what math makes me do. It makes me curious. Did we ever hit 0.42? Yeah, we did. Look at that. Granted, they were the last two, but we did actually 2 out of the 200. So 1%, 2 out of the 200, 1% of them actually had a proportion that high. So what we see is it's not impossible with a population of only 25% being 65 or older to have a sample that looks like that, but it is extremely unlikely. Only 1%. We might even be able to say that we're 99% confident that that sample came from a population that had a higher p than 0.25. All right, well, let's finish up. So today, what we did is we looked at how we can apply inferential statistics to say something about population proportions based on sample proportions, or to say something about a sample proportion, like we did in that last problem, based on sort of a preset population proportion of 0.25. All right. Well, I want to thank you for joining me for another Common Core Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.